Hi, and welcome to my poster presentation on a natural language processing tool offering data extraction for COVID-19 related information, otherwise known as Discovery. My name is Paul Hyder, and I'll be talking to you about work most recently done with my colleagues Ronnie and Stefan at MUSC, the Medical University of South Carolina in the southeastern region of the United States. As part of MUSC's efforts to combat the COVID-19 pandemic, a central database called the COVID Data Mart was designed to collect all electronic health records for patients treated or assessed for COVID-19 at MUSC. The primary means for the general public to be tested at MUSC required using a telehealth application to collect symptoms, medical history, and COVID-19 exposure data. The results of these interactions were included in MUSC's EHR system as natural language generated unstructured text. Initial efforts in March 2020 included the development of a new NLP application prototype to extract COVID-19 related information from this text. Architecturally, we had 4 clusters of machines for this task. The database cluster for reading in notes and writing back structured extracted information, a single server running an Apache UEMA program, specifically UEMA Fit in Java. This Java program also made SSL callouts to a GPU machine for the deep learning named entity recognition components. Finally, there was a log monitoring cluster. Jobs are running automatically at hourly and daily cycles to process all new notes that show up in the data mart. In March of 2020, we deployed an alpha release of this tool with regular patches for performance reasons and general bug squashing. In June of this year, we publicly released an early beta pre-release of Discovery via GitHub in anticipation of a full release in November. Between the alpha and beta releases, we worked on generalizability improvements across all our rule-based and dictionary components, with an eye towards supporting a wider range of note types than that initial telehealth style note we started with. The full release will include a significant increase in machine learning components to further help generalizability, including the addition of machine learning modules for sectionizing, named entity recognition, local context, and hopefully some ensemble methods for combining these models. We're still crunching the data on those right now. If you want to learn more about our machine learning approach to sectionizing, see our other poster on our experiments with support vector machines. Development of our initial prototype was able to be relatively fast at the start because we leveraged a large number of off-the-shelf components, including off-the-shelf modules for reading in plain text notes, pre-processing like tokenizing, our dictionary lookup module, deep learning-based laboratory test name extraction and laboratory test value extraction, medication and medication attribute extraction, concept normalization for both of these, and then relating the medications with their attributes like dosage and frequency. Our dictionary lookup module did require some new lexicons to be generated, but that was handled with a tool called LexGen that we also provide alongside Discovery on our GitHub page. Custom modules were required for reading and writing because of the live production needs of this system, and because we are broadening our usage of the open standards we interfaced with on the database side. The sectionizer was also a new custom module, and the custom demographic and exposure risk extractors had to be made around our needs for COVID. To evaluate our system's performance, we created a corpus of 15 randomly selected clinical notes and had them annotated by domain experts. The stable deployed version of Discovery has higher recall than precision in almost every evaluation category on these 15 notes. As seen in Table 1, the micro averaged F1 measure is about 73, and the macro averaged F1 measure is about 83. The high overlap between COVID-19 symptoms like cough and comorbidities or problems. You can think of all the children of respiratory disease in the UMLS ontology, cause conflicts in our automatically generated lexicon, which hurt our evaluation scores. More work needs to be done to allow control over how lexical entries are assigned to concepts with high overlap. By overlap, I mean overlapping annotations found by different modules in the NLP engine that need to be deduplicated or collapsed or otherwise handled, and overlaps in target concepts to be extracted. We consider Discovery a good example of rapid prototyping to production development and credit that success to a few factors. First, we've been writing our modules towards open standards, which meant refactoring code from old projects was much easier. Because we built on UEMA Fit modules and used their internal CAS-XMI representation, all of our work with sharpened types that were then encoded in the CAS-XMI were fairly easy and flexible. The lexicons are based on UMLS CUIs, and part of our lexicon generation tool is very flexible and easy to deploy and update. And the OMOP CDM for our database structure and database representation. To that last point, keeping the internal representation within the NLP engine separate from the storage model, that is the OMOP CDM schema, allowed us to independently advance work on the engine and downstream modeling efforts simultaneously. One of our major pain points in using this infrastructure in production was tracking multiple pipeline versions across the workflow without doing a full database reprocessing after every upgrade. Thanks for listening. You can contact me at hyderp@musc.edu. Discovery is available at our GitHub page listed on the screen, github.com/musc-tbic/discovery, as well as the TUDE, the tool that we use for evaluation, and LexGen under Lexicon Tools, the tool that we use to generate our UMLS-based lexicons. Thanks for coming.